when we think about conventional biological wastewater treatment, we often think about activated sludge, which is, a suspended growth biological process, usually aerobic, or not always. And the provision of oxygen to that kind of a system is very energy intensive.
Yeah.
I mean, it's like 30% of a municipality's energy consumption can be consumed for aeration. And part of that is because, we typically bubble air through these very deep tanks. And so we need very high power blowers that consume a lot of electricity to do that. Membrane aerated biofilm reactors have modules of like spaghetti-like membranes that are immersed in the bioreactor, and the air is actually provided to the inside of the spaghetti, so blowing through what we call the lumen of the membrane, and oxygen actually diffuses through the membrane out into the solution where the biology is happening, and you actually grow biofilms on the surfaces of those membranes, and that's where a lot of the bioconversions happen. So it becomes the energy efficiency is largely due to the fact that you're not having to expend as much energy to provide oxygen through the membranes compared to having to push it against the water pressure in a deep aeration basin. And so you get savings of energy there. You also get typically a higher percentage of the oxygen that you provide to the system actually gets transferred into the water. So you don't actually have to provide as much air to these systems as well.
Yeah, so when you say, okay, it's a bioreactor and has a membrane, so it has biofilm. And when it comes to a biochemical reaction, typically modeling such process, modeling a conventional bioprocess, it's challenging.
Right.
Because all of those biochemical reactions, physical reactions, and those stuff, when you add with biofilm, I think it's quite challenging.
So we've done quite a bit of work looking at modeling the membrane aerated biofilm reactors. We've collected field data from different aspects of the system to allow us to evaluate the model performance. And most recently, we've been looking at modeling this nitrous oxide emissions, which initially, they come from some of the nitrogen transformations that occurs in the bioreactor. So the approach that we've taken is to model what we call the conventional parameters first. So we've been modeling oxygen consumption and nitrogen, ammonia removal and BOD removal and so on. And we've established that as kind of a baseline for the modeling. And then once we had that, then we added the nitrous oxide biochemical reactions as well as the liquid gas mass transfer reactions to reflect how gases move and so on within this more complex system. So we kind of took a layered approach to the problem and trying to build up from basic to more and more complicated.
We always say there is no magic technology that can solve everything. Right. Every technology has its own challenges. So if you want to highlight, what are the major challenges for this membrane aerated bioreactors?
I think some of the challenges are still going to be associated with low temperature operation. We've seen some changes in performance with low temperatures, and that will continue to probably need more attention as we go on, especially in a Canadian context. We always have to worry about, especially if we're looking at nitrogen removal and so on. But I think that there's progress being made on that. There are some of the issues are just around the things, real practical issues around membranes kind of getting clogged and so on with and maintaining biofilm thicknesses that are not too thick so that we can get good movement of substrates and so on into the biofilms.
Okay.
Yeah.
So, nowadays, I'm quite interested in the artificial intelligence and machine learning because I have two daughters that they are in computer science. So I start to be quite a little bit interested in the computer science and artificial intelligence, and we're doing some work on that. And when I was looking for that, I found that you did some interesting work implementing the artificial intelligence tool and knowledge in your field.
Yeah, we've been working for a few years now looking at, this is with microplastics.
Okay.
And being able to develop improved tools for characterizing microplastics in wastewater systems. So, people have been looking at microplastics for quite some time, but the methodologies for quantifying microplastics are really very different between different studies. So often it's difficult to compare between studies the results because some researchers are just looking at the plastics under a microscope and counting them. Yeah. Some of them are using some advanced microscopy, but the techniques are variable. So when we started looking at microplastics, at the very beginning, we thought, well, we want to have some good tools here for characterizing these plastics. And so we started looking at some advanced microscopy that basically generates three-dimensional kind of images of the microplastics, where you get these fingerprints that tell you something about the composition of the plastic. Right, a spectrogram. And we wanted to be able to take that spectroscopic information and interpret it and to tell us what kind of plastic these particles were. And this is where we started to look at the idea of using some neural network methods for identifying these plastics based upon the imagery that we were collecting with the microscopes. And so we worked actually together with a colleague in systems design engineering here at the university, Alex Wong, to develop an artificial neural network that could identify a range of different plastics. And basically we trained it with some known plastics, and then we tested it on some more complex plastics. And then actually we then went back and kind of trained it a second time with more complex plastics. And so what a lot of people may not realize or know is that plastics are not simple in practice, that they actually, you have what we call the base polymer of a plastic, something like polyethylene, polypropylene, polystyrene. But they often have other kinds of additives in them. So dyes and plasticizers and fillers. And when you use these spectroscopic methods to try and characterize the material, you get smearing of the spectrograms relative to what a simple kind of clean plastic would have. And so what we found was that with the neural networks that we developed, is that they could still recognize the basic plastic that was making up particles despite having these other kind of interfering materials that tended to make the spectrograms more complex and difficult to interpret. They were able to still extract the basic information that was there. And so that, I think it was an interesting use of artificial intelligence. I like to think of it as, I say, artificial intelligence for good, as opposed to some of the other uses that artificial intelligence is being used for. And it helps us, it gave us the ability to have more accurate estimates and also faster data analysis.
So did you give it a name?
It's called PlasticNet.
Plastic nut. I'll remember. Is it a tool that is available for other researchers, or just still?
It's still kind of in the lab, so to speak,
Okay.
right? I think the PhD student that developed it. I think we've talked about trying to perhaps improve the user interface to make it so that it's a little more usable by other practitioners and so on. So I think we will make it available. It's just a matter of that. I think it needs it was developed and built for a particular individual. But often when you have other users, you need to make the interface a little bit more user friendly.